Hello everyone and welcome to chapter 16 where we are going to cover oscillators. Let me try that again. Hello everyone and how the devil are you? Okay, we're going to cover oscillators in this lesson. And if you look right up there, I'm not sure I look up there. Yeah, these are the objectives for this lesson. Describe the operating principles of an oscillator. Discuss the principle on which feedback oscillators is based. Describe and analyze the operation of RC feedback oscillators. Describe and analyze the operation of LC feedback oscillators. Describe and analyze the operation of relaxation oscillators, and discuss and analyze the 555 timer and use it in oscillator applications. Let's pause. All right, so what is an oscillator? It's an electronic circuit. It generates repetitive waveforms, typically sinusoidal or square, without the need for any kind of external input signal. So here are the operating principles of the basic oscillator. Let's go ahead and discuss them, I'll describe them all. Resume recording. There we go, resume recording. So we have two types of oscillators we're going to talk about in this lesson. One of them is feedback oscillators and the other one is relaxation oscillators. But no matter what oscillator we are going to talk about, and we will get into some specific configurations for oscillators, they all have these same basic components. So for example, they all have a feedback loop, and the key element of an oscillator circuit is that feedback loop, and that sends a portion of the output signal back to the input signal. We looked at this when we looked at operational amplifiers. It's a feedback. So this feedback loop is what sustains the oscillation by continuously reinforcing that signal. Otherwise, it would because we have power loss, right? You couldn't sustain it indefinitely. I was going to talk about Newton's conservation of energy and conservation based on Newton's laws of motion, but we don't need to discuss that right now. The next part, or the next phase, is some type of amplification, right? So the oscillator circuit includes an active component such as a transistor, or as you all are familiar with now, operational amplifiers. And we use these to provide amplification to the signal. The amplification compensates for any loss in the circuit, and it also ensures that the output signal maintains its amplitude. Okay. Frequency. There's a frequency component in oscillators, right? So frequency determining components, to be specific, inside the circuits. So these frequency, or the frequency itself, is determined by those specific components, like a resistor, a capacitor, an inductor. And these components, they set the timing of the oscillation cycle. They'll determine the frequency of the output waveform. We also have a phase shift component of the oscillator. And again, I'll get into a little more specifics on each one of these components as we discuss the different types of oscillators. Right now, we're just discussing kind of like the major components of what exists in these oscillators. So there's a phase shift component. And by that I mean that it's just there's an innate phase shifting that occurs. So many oscillator circuits, we have this shift, and it's introduced in the feedback loop. So the phase shift is it's crucial again for sustaining oscillation. So for instance, in a phase shift oscillator where you have an RC network, or you have some active component that's used to create this 180-degree phase shift, that gets fed back into the feedback loop, and then that gets that'll sustain the oscillation. Right? You have some kind of startup component, and you'll hear this referred to as disturbance, a disturbance in the force. So initially, when there's power that's applied to the circuit's turned on, you may not have any oscillation whatsoever. So the oscillator circuit includes a mechanism that will initiate the oscillation. So something like a trigger or some noise source, or like a hammer you hit in the circuit, and then you get the oscillation started. No, we don't use hammers, but that might explain in some cases with some circuits when you kind of like bang them and they all of a sudden start running. No, I'm kidding. That's not the way it works. But Yeah, so the very first time you initiate a circuit for an oscillator, you may have some oscillation or you may not, and there's going to be some trigger that actually gets it started. Right? We have some kind of nonlinear element. So oscillator circuits typically include nonlinear elements. I've been talking so far about linear elements over and over again because we like to design in the linear region so we can be stable and we can be predictable, and most of all we want to be stable and predictable because we want to design something that's safe for the public, right? So you keep hearing me say linear, 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 but here in the oscillator circuit we do have nonlinear elements. And we use this to ensure that the feedback signal is properly amplified and then fed back into the circuit. So these elements will be things like diodes, the transistors that are operating in their nonlinear regions. And you've seen the curve for an operating characteristic curve for a transistor. So this would be transistors operating in the nonlinear regions. And these, again, are crucial for sustaining oscillations. And then we have some kind of control mechanism, right? This is optional, but you should have these anyway. Shall. Thinking about regulations. It's recommended. So oscillator circuits incorporate mechanisms for controlling the frequency or the amplitude of the output waveform. And these control mechanisms that involve things like variable components like potentiometers or voltage control elements. What else? So you can make some really cool things with this. At the very end, or I'll probably save this for class, I'll talk about how I use the 555 timer to create this oscillating ground device that biologists wanted to use to see if it had any effect on cancer cells. So I didn't understand the biology that they were actually looking at, but I built the circuit to do what they wanted it to do. Stability regulation. So you're going to have some kind of stability and regulation as part of your oscillation, as part of your oscillator. So you want to ensure that you have stable, reliable operation. Remember, that's what we do. We're engineers. We design for the public. Reliable, stable, safe. Those two words should equal safety. So you have an oscillator circuit that includes mechanisms for regulating the output waveform's frequency, amplitude. Again, this can include feedback mechanisms to compensate for variations in those component values or some kind of environmental factor. So depending on what the factors are for that device to be operated under. So overall, you're going to have a combination excuse me, of feedback, amplification, frequency determining components, phase shift components, which creates that self-sustaining oscillation within the circuit. And all of this is going to allow it to generate continuous waveforms at some specific frequency. Cool. Next slide. Okay, here we see a diagram where we see a non-inverting amplifier. So you'll have the input and into the non-inverting, and the output, you'll see that it's in phase with the input. So it says here is that the feedback circuit does not invert the amplifier's output. Obviously, it's in phase with the input, and so this produces what's called positive feedback. Positive feedback leads to chaos. All right, I hit the wrong button. Supposed to go to the next slide. There we go. So here we have a feedback oscillator, and okay, in this case, it is out of phase. It's showing here the fraction of the outputs returned to the input with no net phase shift. This means that the feedback circuit compensates for any phase shift in the amplifier and then reinforces the input. So it's an inverting amplifier, and then the feedback inverts the amplifier's output, again producing positive feedback. So the feedback oscillator is a type of oscillator that generates repetitive waveforms. We said that already. Positive feedback occurs when you get that portion of the output signal that's fed back into the input, and what that does, it reinforces the input signal, leading to self-sustained oscillation. Now, if you want an oscillator, that's good. If you want control, positive feedback may not be good. So imagine that you're in your car and you're driving and you want suspension to absorb the shock and provide negative resistance when your car goes up and down, so it'll minimize the effect of that bumping driving in a car. And that's negative feedback, and so it's going to kind of give you this stable compensation for that disturbance. But if you have positive feedback, imagine that your car is driving and it feels like it hit a trampoline, and then instead of like absorbing the energy, more energy is being added to it, and your car's going up and down, up and down. In the 70s, we had cars like that. After the suspension went out, every time you hit a bump, it took a long time for that thing to kind of like settle down. Anyway, but in this case, we want oscillation. So positive feedback in this case is a good thing. Positive feedback in other situations is not always a good thing. So let's go back and talk about some of those components in reference to this slide. So we said feedback loop, right? The core principle of the feedback oscillator, presence of feedback. So what it means is that the loop routes a fraction of the output signal back to the input circuit. The feedback signal, again, is typically phase shift, and it's amplified before being fed back into the input circuit. As you can see here, I don't know if you can see the mouse. Let me see my laser pointer. Yes, laser pointer, nice. All right, so a little signal, amplified, out of phase, big signal, fed back into the input signal. And again, amplification. So amplification. So the feedback loop includes that amplification stage. It boosts the magnitude of the signal. And then this amplification, it compensates for signal loss in the circuit, and it just ensures that the signal maintains that amplitude. Now, because we have this inversion, we're going to have this phase shift. And so the feedback oscillator, the phase shift is introduced into the feedback loop. So the phase shift is, again, crucial for sustaining oscillations. You need this. It ensures that feedback signal reinforces the input signal positively, and it leads to continuous oscillation. And so phase shifts can be achieved using things like RC networks, LC networks, or you can have other active components like operational amplifiers. And we'll look at those toward the very end of this lesson and how they work to sustain oscillations. How does this work? How does this apply this slide to frequency determining components? So again, frequency of the oscillation, again, I said, I'm going to be repeating myself, but it's determined by the specific components in the circuit. Again, we said things like resistors, capacitors, inductors. These components set the timing of the oscillation cycle. They determine the frequency, they determine the output waveform. And then the combination of these components with the phase shift determines the frequency of the oscillation. Nonlinear elements, again, so each time we talk about one of these oscillators, I'm going to go over these components again, and then apply what we're talking about, the concept, to each one of these components. And so it's going to sound like I'm repeating, but there's going to be some slight differences. So just pay attention. That's why I'm recording, because you're going to need to hear this over and over again. Where did I leave off? Nonlinear components. Yeah, nonlinear components. So again, we said these are within a feedback oscillator, right? We're talking about feedback oscillators. They include elements in that feedback loop. Again, they ensure that the signal is properly amplified and is fed back into the circuit. You have nonlinear elements in this case, such as diodes, transistors, and we said again, they're operating in their, or the transistor is operating in its what? In its nonlinear region, right? And again, that is actually crucial for sustaining oscillations. I'll repeat this several times until it sticks, and then I'll try not to repeat it. And then we did say that there is a startup component. So how does this all apply to the startup component, or the startup factor of the oscillation, right? We said when there's initial power, you may or may not have any kind of oscillation. You need some of that feedback to actually, or some kind of disturbance or something to kickstart the process, right? So nothing different right there in the startup when you're dealing with this inverting amplifier out of phase feedback system. But stability and regulation is something we're going to hit on here, right? I didn't mention it in the last slide. So if you want to maintain a stable, reliable operation, the feedback oscillator has to include those mechanisms for regulating the output waveforms, frequency and amplitude. And again, these are going to be involved in controlling the circuit's variation in output based upon the component values variation. And again, depending on the where the circuit, the environment of which the circuit's being operated in, right? So you build a circuit, you design it, you run it in the lab. It runs great in the lab, or it runs as good as you can in the lab. You've optimized it, and it's the best you're going to get. But then when you run these things out in the real world, you're not done with the design. You got to get feedback on how things actually run in the real world, and you're going to this is for any design. You have to optimize your design so that it can you can look and map out the range for environmental factors that where your circuit is going to do what it's supposed to do. Right? So we have a research facility here in town, and they build circuit boards, instrumentation amplifiers, oscillators, things like this that are meant to go to space. And so they use components that were around back in the 60s and 70s. They haven't really updated some of the circuit boards, and there's a very good reason for that, because the components that were designed back then, they're very sturdy, they're bulky, but they can handle a lot of variation in temperature, vibration, and so forth. And so you don't want to test a new circuit with new components when you're trying to send something up in space. So again, they're not going to do a $100 million experiment running a rocket into space with newer components. It takes a long time for them to build to get data to determine whether those components are going to actually react the way they want to in the environment that they're going to work in, right? So, yeah. So when I mentioned last time that you may not be working with discrete components, you'll be working with these integrated chips. That's not entirely true. It just depends on where you work. If you work in the space instrumentation industry, you might think you're going to be working with the most advanced components and technology. It may be that you're working with the most reliable and sturdy technology, which may not be the newest. All right. Okay, so here we see two conditions required for sustained oscillation. The phase shift around the feedback loop must be effectively 0 degrees. And the it says closed loop voltage gain, which is designated by the symbol A and CL, sub CL, meaning closed loop, that has to be greater than 1. And then for a sine wave oscillator, which we see down here, the closed loop gain is equal to exactly 1. Right? So the closed loop gain is equal to the amplifier gain times beta, which is equal to 1. Okay, let's continue with this calculation. So the question is, what is the gain required for the amplifier portion of a sine wave oscillator if the feedback fraction, designated B or beta, I'll say beta for here, is 0.05. Supposed to go to the next slide. There we go. Right, so our formula is A sub CL is equal to AV, the gain, times B, which is the feedback function. And then we isolate for AV, the gain of the amplifier, and that's going to be equal to the closed loop gain divided by the feedback. And that is 1 divided by 0.05. And then we get, oops, went too far. That was supposed to be 20, I think. Okay, this thing doesn't let me go back a slide. All right, so it says feedback oscillators require a small disturbance. I just realized I put these images of myself with the little camera supposed to be up on top, and they're all on the bottom. Anyway, that's beside the point. Right, so feedback oscillators, is the slide here, require a small disturbance such as that generated by thermal noise to start oscillation. This initial voltage starts the feedback process and the oscillations. So I know that a lot of you engineering students, or not a lot of you, some of you have a very creative mind, and you like to stretch some of these principles that we can work with in the lab to something more, I don't want to say metaphysical, because it's not metaphysical, but it borders on something theoretical, right? So think about the start of the universe. I'll get back to the lecture in a minute, but I just want to talk about the start of the universe, right? So the start of the universe had to have had some small disturbance some small, I don't want to say thermal noise because it took something way more than that. Something to start the oscillation for all of existence to be. Right? So, right. Anyway, that just popped in my head. Just wanted to talk to you about that. So think about that after this presentation. All right. So in the context of feedback oscillators, so again, we mentioned the small disturbance, and this can refer to any type of minor, what's called perturbation, some variation in the circuit, some operating condition that potentially affects the stability or the performance of that oscillator. So these disturbances can arise from various sources like changes in temperature. Component tolerances themselves can actually create this disturbance. You can have some small power supply fluctuations, external electromagnetic interference, whether intentional or not intentional. And then when you do have these small disturbances, when they occur in the feedback oscillator circuit, it impacts the amplitude, frequency, the phase of the output of the waveform. So the oscillator circuit is not properly designed to handle those disturbances. They lead to instability, erratic behavior, or even a cessation of the oscillation. So this isn't a case where the positive feedback, in this case, we're using it under certain conditions to sustain oscillations, the positive feedback. But if it's something it was not designed for, I won't say guaranteed to disturb the circuit or disturb the output, but that's a possibility that you will have instability or erratic behavior from the output. Designing feedback oscillators, so they're designed to be robust against very small disturbances. And they typically, when you build these, you need to do something called stability analysis. Now, robust against small disturbances. I mentioned the last slide or 2 slides ago about the space instrumentation research organization that we have here in town that wants our students to work with them, and they talk to us about about some of the constraints that they work with when they're dealing with instrumentation circuit design. And I would classify that as probably not small disturbances, right? I would think that being a circuit that's designed to work in a rocket ship would experience quite a wide variation of disturbances, probably physical disturbances, thermal disturbances, and so forth. All right, so stability analysis. So you're going to conduct a stability analysis, and you do this to understand how those small disturbances affect the oscillator's stability margins. So margins is the word I was trying to think of earlier. And so in this analysis, it can involve techniques like loop gain, phase gain, margin analysis. And what you do is you use this to actually go back and optimize and look at your component selection. So choosing the components with the tight tolerances, low sensitivity to environmental factors, those can actually help minimize the impact of those small disturbances on the oscillator's performance. And when you select or reselect components, then you go back to the same factors for the oscillator and go back to the feedback control. So it's repetitive, it's iterative. So the factors that I mentioned that are built into an oscillator, anytime you do any change, you kind of have to go back to each one of those steps. So when looking at the feedback control, right, you're implementing feedback control to compensate for those small disturbances. You can probably implement something like an automatic gain control, an automatic frequency control. I don't think you've designed those circuits yet, but you will in other classes, or some kind of temperature compensation circuit. Right? I'm sure you're familiar with the temperature compensation circuit. If anybody has climate controls in their home. What else? Oh, so I'll refer back to the space instrumentation department because I'm hoping some of you will end up working there. Isolation and shielding. So in medical, I know there's a lot of ionizing radiation that is ejected from, let's say, an X-ray machine, that can have an effect on the circuit board itself, on the operation of its internal components. If you're in an instrument, if you're an instrument circuit and you're going to space, you'll be needing some different kind of shielding and isolation because you're going to be bombarded with different types of radiation. So what we do is we use techniques such as shielding, filtering, and isolation techniques, and you want to use those to minimize those external interferences on the isolator circuit. And then once you've done this redesign of your oscillator, you test and you verify. Right? Always test and verify. So you thoroughly test the oscillator. You put the circuit under various operating conditions and ensure that it remains stable, reliable under those small disturbances. Now, the very first time I built like a power supply, and I did this in school, I was doing it for a senior project, and I looked at the specs for other power supplies and how they were tested, and this was going to go for our senior design, so we need this power supply to power everything, and we need it to be reliable, and we don't want it to conk out or fail out in the middle of our project. I've seen other power supplies that would have temperature ranges of where these power supplies could operate and how well they operated. So again, this is senior design class. I'm in college. I don't have access to laboratory testing. So I would do things like measure the temperature of my freezer and then run the components in the freezer and just document it that way and determine how well the variances are in my power supply, which are pretty good. But you know, I did stuff like that. But in labs, you're going to have, you may or may not have some sophisticated device that's going to actually alter the environmental factors so that you can, excuse me, oh, that actually looks better than the other light. Cool. Okay, that lighting actually looked a whole lot better. I've seen, again, I don't want to get too sidetracked on here. I've seen testing devices where it's the device is going to be checked for vibration and how it endures during vibration tests, and it really is just it's on a shaker, and so they strap it down and they put the device in, they just turn it on, and the whole thing just physically shaking. And it's like I've seen the pictures where they're held on by like 2x4s and stuff. It doesn't look very sophisticated, but you know, you do the best you can, and maybe that's all that's required for that type of mechanical testing. Okay. All right. And okay, the picture isn't that distracting. So here it says we have a computer simulation on Multisim. It says use digital signals which do not have thermal noise. This often creates a problem for computer simulations of oscillators. Computer simulations. Okay, so just saying that if you run some computer simulations, you're not going to have that thermal noise that's generated when you actually build your real circuit. So because you don't have that thermal noise, which it's a loss in any other circuit, it makes your circuit inefficient. But for oscillation, we kind of want that little noise to come up so that you can actually start the oscillation. So all this slide is saying here is that because on simulations you don't have the practical losses of thermal noise, that you're not going to get the oscillation to commence when you actually simulate this. So you're going to have to figure out a way to actually commence that oscillation. RC feedback, right? So Wein bridge oscillators. I can't go back a slide. This thing doesn't let me go back a slide, so I just, okay. So RC feedback used in various low power applications, okay? Various low power sine wave oscillators, and in our textbook we covered 3 of these. The Wein bridge oscillator, the phase shift oscillator, and the twin T oscillator, and I'll go over those in the PowerPoint. Okay. Right, so here we see the Wein bridge, right? It uses a lead lag circuit. So that means when you have the resistors and the capacitors where they have equal values, not equal to each other, but all the R's are equal and all the capacitors are equal, It says the output's going to be 1/3 of the input at only one frequency, and the phase shift at this frequency will be 0. So you'll have a 0 phase shift, and the amplitude will be 1/3 of the input. And that's where like R1 is equal to R2 and this side, and then C1 and C2 is in the same values. All right. It says Wein bridge uses a lead lag feedback network, and that attenuates, again, just like we said before, the output by 1/3. Gain of the non-inverting amplifier must be exactly 3 times that to produce an output loop gain of 1. So because it's reducing the output by 1/3, when using Wein bridge, you're going to have to create an amplification feedback, and you know how to do this already with operational amplifiers. That's equal to at least, to be exactly 3, right? Not at least, but exactly 3. And that'll give you a gain of 1. Now we talked about this before where we have theoretical and practical components. So it says exactly 3, but we know what that means in the real world. It's as close as you can get it to 3. All right, so a little bit more about the Wein bridge lead lag feedback. So it says non-inverting amplifier gain is set by R1 and R2, and R1 and R2 is there at the input of the inverting input for the amplifier. And so if the gain is too little, oscillations won't occur. If it's too much, a sine wave will be clipped. So we're going to clip some of the oscillation. Just in the basic circuit shown, it is nearly impossible to set the gain to be precise to the precise value required. Right? Nearly impossible, not impossible, difficult. And like I said before, theoretical, definitely you can calculate this to come out perfect. In a simulation, you'll be able to run it on a simulation, but if you try to get this on a practical circuit, on a breadboard, it's gonna require some finesse. And then again, to produce the precise gain required, the Wein bridge needs some form of automatic gain control. And then this is one popular method. If you look there in the highlighted, the yellowish, greenish highlighted area there, where they use a JFET transistor. So think about like the JFET amplifiers, where you're replicating an input signal to the output, but in this case, we're taking the output of the Wein bridge. We're running it through a running it as a feedback to the amplifier so that you can have what's called automatic gain control. All right, give me 1 second. Okay, pardon me for that phone call. All right, so the Wein bridge oscillator, right? So this is a type of oscillator circuit. It's commonly used to generate sine waves in audio frequencies. What else? Audio. I can't think of a use where it would have an application, let's say in medical, even though we do use oscillators in quite a few medical devices, from ultrasound, the thermal radiation therapy devices, MRIs, did I say ultrasound already? Yeah, ultrasound, Doppler, but not Wein bridge. Right? We use this for the audio frequencies, which is much lower. The Wein bridge oscillator, again, it's just a network of resistors, capacitors, and we use this to achieve that particular type of oscillation. It's also not very tight. That's why we don't use these in medical. Maybe in the alarm settings of medical devices, but yeah. So the basic configuration of a Wein bridge, it consists of an amplifier, and it's usually an op-amp. You're going to have some kind of bridge network that's composed of, again, 2 resistors, 2 capacitors, and they have a very specific configuration, which you see there in the highlighted part of the image. So the bridge network, that forms this feedback loop, and it typically is made up of 2 voltage dividers. They're connected in parallel. One One divider is basically a resistor and a capacitor in series, while the other divider consists only of a resistor. There's a junction between the resistor and the capacitor in the first divider, and the junction between the two resistors in the second divider. Those are connected to the input and output terminals of the amplifier, so respectively. The feedback mechanism, this factor of the oscillator. So I said I was going to be hitting each one of these factors as we talk about the different types of oscillators. There's a bridge network. It provides the positive and negative feedback to the amplifier. At some desired oscillation frequency, you can have a phase shift around that loop. Would you try to maintain a zero? Again, theoretically, but ideally no. It's going to lead to some kind of positive feedback. The phase condition, this occurs when the impedance of that resistor capacitive series network equals the impedance of the resistor in the other arm of the bridge. So you can use this for design to determine what your values are going to be. And what this does, it balances it provides balance there. I'll say that. I don't think I said it right, but it's close enough, close enough. So frequency determination. We talked about this as a factor for oscillators. We have to determine the frequency, determine the amplitude. I really hope that this is picking up my voice because I haven't tested it and made sure that you can hear me. Frequency determination. So the frequency of the oscillation in that Wein bridge. Wein bridge just sounds so good. Wein sitting on a bridge. It's determined by the values of the resistors, again, capacitors in that bridge network. And then the oscillator's frequency is given by that standard formula of 1/2 pi RC, right? Which I don't have it here. Yeah, frequency is equal to 1/2 pi RC, right? Yeah, I'm sure it is. So you adjust either the resistor or the capacitor values, and then you can tune the oscillator to the desired frequency. Now let's go to the amplifier stage. How is this affected here? Within the Wein bridge oscillator, it provides gain, again, to compensate for the losses in the bridge network, because you are going to have losses. Practically, theoretically, no. Practically, always, yes. So we're moving in baby steps. So you compensate for those losses in the bridge network. You have to do that because you've got to maintain those losses so you can sustain continuous oscillation in the feedback, from the feedback, right? So it ensures that you have that constant amplitude over that wide range of frequencies. Now we talked about automatic gain control, AGC, and so a little bit more into that, right? In some implementations of AGC, you're going to have the circuit that also helps stabilize the amplitude of the oscillator's output signal, which takes us to the last part, which is stability and then tuning. So Wein bridge oscillators, you can make them to be very, very stable, somewhat. Just got to pay attention to the component tolerances, because remember, we've talked about tolerances and components and their values and how they deviate when they're in different environments, right? So temperature being one of them. So the temperature stability of certain components will change the value of those components. And so a typical resistor with 20% variance, that's a lot of variance, right? If it's necessary for the stability of the oscillation. And I mean the frequency and the amplitude of that. So you try to use components that have tighter tolerances, as much as you can afford. That's always going to be the problem. As much as your project can afford, right? It may be that you have to use cheaper components, not resistors. Those things are super cheap, but you get the idea. You may have to make compromises. So again, tuning the oscillator to whatever desired frequency you want is going to require precise adjustments of those resistors and then those capacitor values. So you don't want to use something like you'll see the feedback resistor in this circuit, the potentiometer. Those are not very precise, and they vary widely based on the environmental factors. So that is not something you'd want to use if you want to have a very precise value of tuning with your Weinberg oscillator. So you can use a potentiometer to tune it to where you need it to be, and then you can actually design it with the physical components that are stable, static. So overall, the Weinberg oscillator, it's a versatile circuit. It's used often in audio signal generation. It's good because it has very low distortion, and it can produce sine waves at very precise frequencies. Again, in the audio range. All right, so here we just see a characteristic graph of the JFET, and it's operated in this ohmic region. This can change its resistance rapidly if condition changes. So this is just talking about the component tolerances and how they're affected by environmental factors. Now, if you have this as a feedback, you can have this automatically compensate for your feedback depending on your environment. Pretty cool. Okay. So a JFET, right? Junction field effect transistor, when it's operating in that ohmic or the linear region, that just means that the transistor, it's biased so that the channel conducts current with that linear relationship between the input voltage and the output current. So this is how the JFET works in that region. So biasing, if you remember this from your previous class or previous courses. So the JFET, it's biased with the voltage applied between the gate and the source terminals. And when it's in that ohmic region, the bias voltage, typically it's set so that the gate source voltage is below the JFET's threshold. So for example, if you have an N-channel JFET, this just means the gate is negative with respect to the source. If you look at the channel conductance of the JFET, which should be below the threshold voltage, the depletion region between that gate and the channel, that remains wide. And then the channel between the drain and the source is only, if you remember from your textbook, weakly pinched off, right? So it pinches that current. So what this does, it allows the current to flow through the channel, and then the JFET operates as this voltage-controlled resistor. Now, the linear relationship of this to the operation of the oscillator. So when it's in this ohmic region, that relationship between that input voltage and the output current, it's approximately linear. So this just means that you have a small change in the gate source voltage, and that results in something proportional in the drain current. So the JFET starts behaving like a variable resistor, and its resistance can be controlled by the gate source voltage. So you can see we get this automatic gain feedback control through the JFET, and it can be extremely precise versus the image that you saw in the previous slide, and you'll see again in a couple more slides, where you have what looks like to be a schematic symbol for a potentiometer, and you don't really want that. So JFETs are awesome. Looking at the drain to source voltage, the drain to source voltage plays a role in the JFET operation. So again, when we're in the ohmic region, it should be kept sufficiently low to maintain the JFET in that linear operating region. If it becomes too high, what happens if it becomes too high? Then the JFET enters that saturation region, if you can remember this from your previous courses, chapters. And what happens is the drain current becomes relatively insensitive to the changes, basically, when it's saturated. So in other words, you're not going to get any change in the current with any change in the input. So it becomes useless, and you don't want it running there. Where do you see this? So I feel like I'm doing a podcast. Oh, so you're asking me, when are we ever going to see this? Let me talk to my viewers. No, I should do a podcast. So JFETs, right? They're operated in this particular case in the ohmic region, and they're commonly used in circuits where you have voltage controlled amplifiers, and so they act like variable resistors to control the gain. I can't guarantee this is where the circuit is actually found, but I'm just thinking of a very good application where you're going to be dealing with audio frequencies. Again, I'm not guaranteeing that this is what the circuit looks like or this is what it is, but an automatic gain control device we're talking about automatic gain control. The automatic gain function on your TV or your car stereo that maintain that smart sound system, right? So it doesn't get too loud, too soft. It might be something like this. If it's not, you could probably design something like this to work. It may not be the best, or maybe exactly what you need. So again, operating the JFET in that ohmic region, it allows for that precise control of conductance, and it just makes it very useful where linear amplification signal processing is required. Oh wow, we got a lot of slides to go through. So here we have an image where we have the JFET in the circuit, highlighted there in blue. We have R's and C's, the resistors and capacitors, and the feedback circuit, and they're equal to the frequency of the bridge, and that's given by that formula, 1 over 2 pi RC. And then we got an example here. I'm going to go real quickly through this, and then you can slow it down later to try to understand it. So what is the frequency for the Wein bridge given here? It says the solution is 1 over 2 pi RC. If we look at the components, it's we got 680 for the resistance, 4.7 nanofarads for the capacitor. So 1 over 2 pi times 680 times 4.7 nanofarads. I'm going to click this once. Hopefully I won't pass the answer. 48.9 kilohertz. So that would be the frequency for the Wein bridge. All right, phase shift oscillators. So let's talk about phase shift oscillators, where we said Wein bridge, phase shift, and twin T. So the phase shift oscillator, it's a type of electronic oscillator, and it generates sinusoidal output signals. It relies on, again, another RC network, and it is used to create phase shifts in the feedback loop. And when you combine this with an amplifier, this results in that sustained oscillation. Right. So how does that work, you're asking? Well, let's go back to the components. So in the feedback network portion, right, the heart of that phase shift oscillator is the feedback network, and that introduces phase shifts to the output signal, just like we mentioned before. So that part isn't any different. The abstract operation of the feedback oscillator. Again, network is made up of multiple RC components, resistors, capacitors. Each stage, in this case, introduces a phase shift in the signal, usually around 60 degrees, at some desired oscillation. So you can see we have 3 duplicates of an RC network there, each one about 60, right? 60, 60, 60. That's going to be 180. And that'll give us the 180 degree phase shift that we need back for the input, right? So that phase shift, the next factor for the oscillator, across each RC stage frequency, is frequency dependent. So the oscillation frequency, the combined phase shift around the total loop is 360 degrees, right? So that's the condition required for positive feedback if you have an oscillating circuit in this case. Let's talk about the amplification. So we have, again, you need amplification. I got a headache. And again, often it's going to be an operational amplifier, even though you can build this with standard transistors, discrete components. But we use an operational amplifier, and we need that because we need to compensate for signal losses that is inherent in the feedback network. We're always going to have losses, and that's necessary, right, to improve the gain, and it's necessary to that's necessary in the feedback to sustain continuous oscillation. So you need that over and over and over again. I've said that like 20 times already. So if that's like in a test somewhere, it's not, but the test of life One day you'll remember that. So he kept saying that. Kept saying that the amplification in the oscillation circuit is necessary to sustain oscillations, future oscillations. And then one day it's just gonna like epiphany. You're gonna be like, I get it. So the amplifier amplifies the phase shifted signal because it's phase shifted, feeds it back to the input of the network. Frequency determination in this case, it's primarily determined by the time constants of the RC stages in that feedback network that you see there highlighted in green. So the oscillation frequency, you can calculate this using that formula. It's 1/2 pi RC times 6. We'll see it on the next slide, hopefully. Don't quote me on that. Remember we talked about startup, right? So you need some kind of initial disturbance in the force to get these things to move. So when you initially turn on power to this circuit, the oscillator is turned on, but you may not have any oscillations. If you do this in simulation and you see nothing, well, read the lab procedure again, because you're probably missing a step there to create artificially that disturbance. So here, if you have something, some small noise or disturbance in the practical circuit, in the breadboard circuit, that's enough to actually initiate the oscillations. The circuit starts into its oscillation and then it goes into a stable oscillation mode. Right? What else? What else? What else? Tuning the circuit. That's it. That's all, right? So the phase shift oscillation, it's used widely in applications that require a very steady sinusoidal signal. Again, audio oscillators are a good application for this. Tone generators, frequency synthesizers. They offer a very simple design, very low distortion. They have relatively good frequency stability compared to other oscillator configurations. So it's good. I mean, look at this. It's very, very simple to build. That's if you don't have access to like crystals. And we'll talk about crystals at the end of this lesson. All right, so conditions for oscillations with the phase shift oscillators is all R's and C's are equal. The amplifier must have a gain of at least 29 to make up for the attenuation of the feedback circuit, which in this case it's RF divided by R3 greater than 29. So we have a reduction of attenuation of 29. So we need to actually make that sure that the gain is at least 29. And this is the formula I was trying to think of. Under the conditions, the frequency of the oscillation is given by 1/2 pi RC times the square root of 6. And hopefully, if you're listening to this and not seeing this, let me make sure I said that correctly. 1/2 pi times the square root of 6 R times C. 1 over all of that. Okay. All right, my little pictures up there. Multi-sim, I'm going to go ahead and skip the multi-sim simulation slides. All right. This is just how to wire it up for the lab. And then I'll go over the example, and then I'm actually going to cut this presentation and do a second part, because this is very, very long. Design a phase shift oscillator for a frequency of 800 Hertz. The capacitors are to be 10 nanofarads. All right. So solving for the resistors needed in the feedback circuit, we can rearrange the equation algebraically to solve for R. R is equal to 1/2 pi square root of 6 FR times C. And so we plug in the numbers. We can say plug and chug. Oh, sorry. I can't record more than 30 minutes because then the lights turn off. Where did I leave off? Yeah, so we end up with 8.12 kilo ohm, or we can round up to 8.2 kilo ohm, since 8.2 is a standard value for resistors. It says calculate the feedback resistor needed. So the RF is, since it's got to be 29 times R, it's going to be 238 kilo ohms. And here's what the circuit will look like. Right, 238 kilo ohms for the feedback resistor, 8.2 kilo ohms for the resistor in the RC network. And that's it. Following slide shows multi-sim check. So I'm just going to go ahead and click to the multi-sim slides so that we can get rid of those. And I'm going to start a part 2, continuing with oscillators. So that is the multi-sim. All right, thank you very much for your time. It's about 55 minutes for this lecture. We will continue with part 2 of oscillators when I cover the twin T oscillator, and we're going to combine that with low pass and high pass filters to form notch filters and oscillation, specific oscillation frequencies. Thank you very much. See you in part 2.